Saturn is the sixth planet from the Sun, and the second largest in the Solar System, after Jupiter. It is a gas giant, with an average radius about 9 times that of Earth, although only 1/8 the average density of Earth. With its larger volume, Saturn is just over 95 times more massive. Saturn is named after the Roman god of agriculture. Its astronomical symbol represents the god's sickle. Saturn's interior is probably composed of a core of iron, nickel and rock. This core is surrounded by a deep layer of metallic hydrogen, an intermediate layer of liquid hydrogen and liquid helium, and finally outside the Frenkel line a gaseous outer layer. Saturn has a pale yellow hue due to ammonia crystals in its upper atmosphere. Electrical current within the metallic hydrogen layer is thought to give rise to Saturn's planetary magnetic field, which is weaker than Earth's, but has a magnetic moment 580 times that of Earth due to Saturn's larger size. Saturn's magnetic field's strength is around 1/20th of Jupiter's. The outer atmosphere is generally bland and lacking in contrast, although long-lived features can appear. Wind speeds on Saturn can reach 1,800 km per hour, higher than on Jupiter, but not as high as those on Neptune. Saturn has a prominent ring system that consists of 9 continuous main rings and 3 discontinuous arcs, and that is composed mostly of ice particles with a smaller amount of rocky debris and dust. 62 moons are known to orbit Saturn, of which 53 are officially named. This does not include the hundreds of moonlets comprising the rings. Titan, Saturn's largest moon, and the second largest in the Solar System, is larger than the planet Mercury, although less massive, and is the only moon in the Solar System to have a substantial atmosphere. Physical characteristics. Saturn is a gas giant because it is predominantly composed of hydrogen and helium. It lacks a definite surface, though it may have a solid core. Saturn's rotation causes it to have the shape of an oblate spheroid, that is, it is flattened at the poles and bulges at its equator. Its equatorial and polar radii differ by almost 10%. 60,268 km versus 54,364 km, respectively. Jupiter, Uranus, and Neptune, the other giant planets in the Solar System, are also oblate but to a lesser extent. Saturn is the only planet of the Solar System that is less dense than water, about 30% less. Although Saturn's core is considerably denser than water, the average specific density of the planet is 0.69 grams per cc due to the atmosphere. Jupiter has 318 times the Earth's mass, while Saturn is 95 times the mass of the Earth. Together, Jupiter and Saturn hold 92% of the total planetary mass in the Solar System. On the 8th of January 2015, NASA reported determining the center of the planet Saturn and its family of moons to within 4 kilometers. Internal structure. Despite consisting mostly of hydrogen and helium, most of Saturn's mass is not in the gas phase. Because hydrogen becomes a non-ideal liquid when the density is above 0.01 grams per cc, which is reached at a radius containing 99.9% of Saturn's mass. The temperature, pressure, and density inside Saturn all rise steadily toward the core, which, in the deeper layers, cause hydrogen to transition into a metal. Standard planetary models suggest that the interior of Saturn is similar to that of Jupiter, having a small rocky core surrounded by hydrogen and helium with trace amounts of various volatiles. This core is similar in composition to the Earth but more dense. Examination of Saturn's gravitational moment, in combination with physical models of the interior, allowed French astronomers Didier Somon and Tristan Gillet to place constraints on the mass of Saturn's core. In 2004, they estimated that the core must be 9 to 22 times the mass of the Earth, which corresponds to a diameter of about 25,000 kilometers. This is surrounded by a thicker liquid metallic hydrogen layer, followed by a liquid layer of helium-saturated molecular hydrogen that gradually transitions to a gas with increasing altitude. The outermost layer spans 1,000 kilometers and consists of gas. Saturn has a hot interior, reaching 11,700 degrees Celsius at its core, and it radiates 2.5 times more energy into space than it receives from the Sun. Jupiter's thermal energy is generated by the Kelvin-Helmholtz mechanism of slow gravitational compression. But this alone may not be sufficient to explain heat production for Saturn, because it is less massive. An alternative or additional mechanism may be generation of heat through the raining out of droplets of helium deep in Saturn's interior. As the droplets descend through the lower density hydrogen, the process releases heat by friction and leaves Saturn's outer layers depleted of helium. These descending droplets may have accumulated into a helium shell surrounding the core. Atmosphere. The outer atmosphere of Saturn contains 96.3% molecular hydrogen and 3.25% helium by volume. The proportion of helium is significantly deficient compared to the abundance of this element in the Sun. The quantity of elements heavier than helium is not known precisely, but the proportions are assumed to match the primordial abundances from the formation of the Solar System. The total mass of these heavier elements is estimated to be 19 to 31 times the mass of the Earth, with a significant fraction located in Saturn's core region. Trace amounts of ammonia, acetylene, ethane, propane, phosphine and methane have been detected in Saturn's atmosphere. The upper clouds are composed of ammonia crystals, while the lower-level clouds appear to consist of either ammonium hydrosulfide or water. Ultraviolet radiation from the Sun causes methane photolysis in the upper atmosphere, leading to a series of hydrocarbon chemical reactions with the resulting products being carried downward by eddies and diffusion. This photochemical cycle is modulated by Saturn's annual seasonal cycle. Cloud layers. Saturn's atmosphere exhibits a banded pattern similar to Jupiter's, but Saturn's bands are much fainter and are much wider near the equator. The nomenclature used to describe these bands is the same as on Jupiter. Saturn's finer cloud patterns were not observed until the flybys of the Voyager spacecraft during the 1980s. Since then, Earth-based telescopy has improved to the point where regular observations can be made. The composition of the clouds varies with depth and increasing pressure. In the upper cloud layers, with the temperature in the range 100 to 160 K and pressures extending between 0.5-2 bar, the clouds consist of ammonia ice. Water ice clouds begin at a level where the pressure is about 2.5 bars and extend down to 9.5 bars, where temperatures range from 185 to 270 K. Intermixed in this layer is a band of ammonium hydrosulfide ice, lying in the pressure range 3 to 6 bars with temperatures of 290 to 235 K. Finally, the lower layers, where pressures are between 10 to 20 bars and temperatures are 270 to 330 K, contains a region of water droplets with ammonia in aqueous solution. Saturn's usually bland atmosphere occasionally exhibits long-lived ovals and other features common on Jupiter. In 1990, the Hubble Space Telescope imaged an enormous white cloud near Saturn's equator that was not present during the Voyager encounters, and in 1994, another, smaller storm was observed. The 1990 storm was an example of a great white spot, a unique but short-lived phenomenon that occurs once every Saturnian year, roughly every 30 Earth years, around the time of the Northern Hemisphere's summer solstice. Previous great white spots were observed in 1876, 1903, 1933 and 1960, with the 1933 storm being the most famous. If the periodicity is maintained, another storm will occur in about 2020. The winds on Saturn are the second fastest among the Solar System's planets, after Neptune's. Voyager data indicate peak easterly winds of 500 meters per second. In images from the Cassini spacecraft during 2007, Saturn's northern hemisphere displayed a bright blue hue, similar to Uranus. The color was most likely caused by Rayleigh scattering. Thermography has shown that Saturn's south pole has a warm, polar vortex, the only known example of such a phenomenon in the Solar System, whereas temperatures on Saturn are normally -185 degrees Celsius. Temperatures on the vortex often reach as high as -122 degrees Celsius. Suspected to be the warmest spot on Saturn. North Pole hexagonal cloud pattern. A persisting hexagonal wave pattern around the north polar vortex in the atmosphere at about 78 degrees north was first noted in the Voyager images. The sides of the hexagon are each about 13,800 kilometers long, which is longer than the diameter of the Earth. The entire structure rotates with a period of 10 hours 39 minutes 24 seconds, which is assumed to be equal to the period of rotation of Saturn's interior. The hexagonal feature does not shift in longitude like the other clouds in the visible atmosphere. The pattern's origin is a matter of much speculation. Most scientists think it is a standing wave pattern in the atmosphere. Polygonal shapes have been replicated in the laboratory through differential rotation of fluids. South Pole Vortex HST imaging of the South Polar region indicates the presence of a jet stream, but no strong polar vortex nor any hexagonal standing wave. NASA reported in November 2006 that Cassini had observed a hurricane-like storm locked to the South Pole that had a clearly defined eye wall. Eye wall clouds had not previously been seen on any planet other than Earth. For example, images from the Galileo spacecraft did not show an eye wall in the Great Red Spot of Jupiter. The South Pole storm may have been present for billions of years. This vortex is comparable to the size of Earth, and it has winds of 550 km per hour. Other features. Cassini has observed a series of cloud features nicknamed string of pearls, found in northern latitudes. These features are cloud clearings that reside in deeper cloud layers. Magnetosphere. Saturn has an intrinsic magnetic field that has a simple, symmetric shape, a magnetic dipole. Its strength at the equator 0.2 Gauss is approximately 1/20th of that of the field around Jupiter and slightly weaker than Earth's magnetic field. As a result, Saturn's magnetosphere is much smaller than Jupiter's. When Voyager 2 entered the magnetosphere, the solar wind pressure was high and the magnetosphere extended only 19 Saturn radii, or 1.1 million km, although it enlarged within several hours, and remained so for about 3 days. Most probably, the magnetic field is generated similarly to that of Jupiter, by currents in the liquid metallic hydrogen layer called a metallic hydrogen dynamo. This magnetosphere is efficient at deflecting the solar wind particles from the Sun. The Moon Titan orbits within the outer part of Saturn's magnetosphere and contributes plasma from the ionized particles in Titan's outer atmosphere. Saturn's magnetosphere, like Earth's, produces aurora, orbit and rotation. The average distance between Saturn and the Sun is over 1.4 billion kilometers. With an average orbital speed of 9.69 km per second, it takes Saturn 10,759 Earth days to finish one revolution around the Sun. The elliptical orbit of Saturn is inclined 2.48 degrees relative to the orbital plane of the Earth. The perihelion and aphelion distances are, respectively, 9.022 and 10.053 astronomical units, on average. The visible features on Saturn rotate at different rates depending on latitude, and multiple rotation periods have been assigned to various regions. Astronomers use 3 different systems for specifying the rotation rate of Saturn. System I has a period of 10 hours 14 min 00 second, encompasses the equatorial zone, the south equatorial belt and the north equatorial belt. The polar regions are considered to have rotation rates similar to System I. All other Saturnian latitudes, excluding the north and south polar regions, are indicated as System 2 and have been assigned a rotation period of 10 hours 38 min 25.4 sec. System 3 refers to Saturn's internal rotation rate, based on radio emissions from the planet in the period of the Voyager flybys. It has been assigned a rotation period of 10 hours 39 min 22.4 sec. Because it is close to System 2, it has largely superseded it. A precise value for the rotation period of the interior remains elusive. While approaching Saturn in 2004, Cassini found that the radio rotation period of Saturn had increased appreciably, to approximately 10 hours 45 min 45 sec. The latest estimate of Saturn's rotation, based on a compilation of various measurements from the Cassini, Voyager and Pioneer probes, was reported in September 2007 as 10 hours 32 min 35 sec. In March 2007, it was found that the variation of radio emissions from the planet did not match Saturn's rotation rate. This variance may be caused by geyser activity on Saturn's moon Enceladus. The water vapor emitted into Saturn's orbit by this activity becomes charged and creates a drag upon Saturn's magnetic field, slowing its rotation slightly relative to the rotation of the planet. Planetary rings. Saturn is probably best known for the system of planetary rings that makes it visually unique. The rings extend from 6,630 kilometers to 120,700 kilometers outward from Saturn's equator, average approximately 20 meters in thickness, and are composed of 93% water ice with traces of tholin impurities and 7% amorphous carbon. The particles that make up the rings range in size from specks of dust up to 10 meters. While the other gas giants also have ring systems, Saturn's is the largest and most visible. There are two main hypotheses regarding the origin of the rings. One hypothesis is that the rings are remnants of a destroyed moon of Saturn. The second hypothesis is that the rings are left over from the original nebula material from which Saturn formed. Some ice in the E-ring comes from the moon Enceladus's geysers. In the past, astronomers once thought the rings formed alongside the planet when it formed billions of years ago. Instead, the age of these planetary rings is probably some hundreds of millions of years. Beyond the main rings, at a distance of 12 million km from the planet, is the sparse Phoebe ring, which is tilted at an angle of 27 degrees to the other rings and, like Phoebe, orbits in retrograde fashion. Some of the moons of Saturn, including Pandora and Prometheus, act as shepherd moons to confine the rings and prevent them from spreading out. Pan and Atlas cause weak, linear density waves in Saturn's rings that have yielded more reliable calculations of their masses. Natural satellites. Saturn has at least 150 moons and moonlets, 53 of which have formal names. Titan, the largest, comprises more than 90% of the mass in orbit around Saturn, including the rings. Saturn's second largest moon, Rhea, may have a tenuous ring system of its own, along with a tenuous atmosphere. Many of the other moons are small, 34 or less than 10 kilometers in diameter, and another 14 between 10 and 50 kilometers in diameter. Traditionally, most of Saturn's moons have been named after titans of Greek mythology. Titan is the only satellite in the Solar System with a major atmosphere, in which a complex organic chemistry occurs. It is the only satellite with hydrocarbon lakes. On 6 June 2013, scientists at the IAA-CSIC reported the detection of polycyclic aromatic hydrocarbons in the upper atmosphere of Titan, a possible precursor for life. On 23 June 2014, NASA claimed to have strong evidence that nitrogen in the atmosphere of Titan came from materials in the Oort cloud, associated with comets, and not from the materials that formed Saturn in earlier times. Saturn's moon Enceladus, which seems similar in chemical makeup to comets, has often been regarded as a potential habitat for microbial life. Evidence of this possibility includes the satellite's salt-rich particles having an ocean-like composition that indicates most of Enceladus's expelled ice comes from the evaporation of liquid salt water. In April 2014, NASA scientists reported the possible beginning of a new moon within the A-ring of the planet Saturn, which was imaged by Cassini on 15 April 2013.